Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. And today's topic we will see the FVM and FDM for shock capturing techniques. Okay, so basically, what is FVM? So FVM is nothing but finite volume method. FDM is nothing but finite difference method. So we have a shock. So basically, which is formed because of collection of all weak sound waves. So how do we capture, whether we can capture using finite difference method or finite volume method, we'll just see actually. So to have a recall, so these things we have seen where the finite volume method is applicable for complex geometry and the integral form of equations are used for finite volume method. Okay, so here if we take this grid phenomena, so when we place a shock here, so let's say this is a shock, fine. So whether a FDM method or FVM method is able to predict properly about shock or not. So whether integral form of equation or only differential form of equation can be used to capture the shock or not. These things we are going to say. So before that, we have seen for 1D flow, and this is the basic equation which we have seen, the divergence of the diffusion term and the source term. Then we need to actually see how to capture the shock. So let's say first of all, what is a shock we will see. Then how do we capture the shock we will see. So let us take this as wedge. So these are some angle theta, fine. So a flow which is coming, let's say Mach number m infinity. So what is Mach number? So Mach number m infinity is nothing but so v infinity by a infinity. Let's say. So what is v infinity? So the speed of the object or the speed of the flow divided by sound, speed of the sound in the medium. So let's say if you have in water, so what is the speed of sound in water or vacuum? So what is the speed of sound in vacuum? So these aspects here. So when Mach number is greater than 1, we say the flow as supersonic. Fine. Already we have seen when Mach number is less than 1, so we have seen the flow as subsonic. So in detail, in detail classification, we have M, which is less than or equal to 1.2, greater than or equal to 0.8. So this is called transonic flow actually. So transonic flow in the sense you have some areas or some regions on the geometry with subsonic and some regions of the geometry supersonic. Okay, so that's why we call it as transonic. Fine. So here what is happening? So when you have, let's say, Mach number in precise greater than 1.2, so everywhere on the geometry or let's say on the body, so the flow is supersonic everywhere. So at all the locations, all the points. In the transonic, what happens? So let's take an example of airfoil. Fine. So for this airfoil, what do we have? So we have a weak flow, so which is a normal shock which is formed. So here the Mach number will be less than 1. Here let's say it is greater than 1. So some region here it is less than 1. Some here and here it is greater than 1. Okay, this is what we have. Fine. So these are the basic examples where you can say that a flow is fully neither subsonic nor supersonic actually. So it is the combination of subsonic and supersonic. So what do we have? Like in subsonic, the load acting on the body will be, let's say, some x, and in supersonic the load will be acting, let's say, x plus delta x. So what happens? There is a differential load which is happening, and you have the unsteadiness and oscillations which is formed over the geometry. So here we have taken the example of airfoil. Okay. Now, so what happens actually? So when we want to see the shock fitting and shock capturing, capturing in the sense what? So let's say you have shock here. Okay. So this is wall. Okay, so when you draw the mesh, so we need to able to capture this shock. So this is the aspect. Fine. So here, what should be the dimension of the mesh such that we capture the shock? So that is very, very important. Fine. So this is what we have. Okay. So here, what is happening? We need to mesh the shock. So here, let's say this is the thin layer. So this is a thin, very thin layer. So you need to precisely space the spacing of the grid point such a way that you capture the shock. Okay, so this is one technique, and the other technique what we have is fitting. So fitting in the sense what? So shock, we know where exactly the shock is formed. So let us take this as wedge again. So here m is greater than 1. So we have a shock like this. So in this, before starting simulation, let's say if you know that the shock, okay, so shock wave is present at particular location. So what we do is that so as a part of solution, so the mesh will be performed here actually. Okay, so the shock will be as a part of solution. So this is one type of technique. So in the both the technique, so basically what happens for FVM and FDM, so that we need to see. So if you see a normal shock, so there are two types of shock. One is called normal shock, other one, so this is called normal shock. So this is station 1 and this is station 2. Okay, so this is called normal shock. Okay, so other thing, so we have oblique shock. Fine. So when we see this one, let us draw again. So this is called oblique shock. So here you have, this is station 1, here you have station 2. Okay, so this is called oblique shock. So one we have normal shock, other one we have oblique shock. So which method is preferable, whether the finite volume method, finite difference method is preferable to capture the shock? Okay, so that thing we see. So it is considered a normal shock. So first, how a shock is formed is, so when the speed of the flow is crossing or surpassing, or let's say it is overcoming the speed of sound. So what is happening? All weak, so what weak sound waves will join together and form a wave called shock wave. So what is happening? Like when the flow is subsonic, so the body velocity and the speed of sound velocity when you compare, so this will be higher and this will be lower. Fine. So the flow can the sound waves will be transmitted in all the regions such that it has sufficient time. Okay, now when it is crossing, when the speed of, like, let's say the velocity of the object is crossing speed of sound, then what happens? There will be some reaction, or let's say there will be some natural effects where the uh, weak waves, so when speed of object is greater than speed of sound, so we call the sound waves as weak waves. Those weak waves will join, will come together and will join and form a strong wave. Okay, so this form of wave is called the shock wave, SW. Fine. So this shock wave, actually what it does, it try to decelerate the velocity of the object. So the major agenda is to overcome the speed of object. So it's like a marathon between, so velocity of object and speed of sound. So when speed of, this is coming from the natural effect. So this is from the human effect, let's say. So when humans, or let's say aircraft, trying to overcome the speed of sound, so initially you'll have the sound barrier. Okay, so in the transonic zone, so initially people used to think that the sound barrier is a kind of a blasting thing. So we cannot cross that, and if we cross, we will have major disasters. So people thought that. So it was a myth actually. So as the time progressed, so people has crossed the sound barriers and they have went to supersonic speeds, and then they are going for hypersonic speeds also. Okay, even high hypersonic speeds, manned machines are there actually. Fine. So these aspects are present. Now, what is happening? So when you have this strong shock wave, the properties of the flow will change suddenly like this. So here you have P1. So suddenly at this point, so it will rise and it will go to P2. Fine. So shock thickness will be somewhat microns. So it is of very negligible thickness. So it does not have a large amount of thickness. And here the shock wave. So whatever we have, so it is very thin. Fine. So even we cannot see with our naked eyes to see like shock. We need to have some flow visualization technique like Schlieren, shadow graph to see the shock actually. Now, since the thickness of shock is very less, let's say it is of 10 power minus 6 or 10 power minus 5 meters, so the grid or the mesh which it has to capture, so that will be very fine mesh actually. So the spacing should be nearly equal to this aspect, fine. Or we apply some techniques to capture this shock. Fine. So now the problem is, so it's like a point. So when you see in reality, so it's a point where suddenly there is a flow change. So this discontinuity is happening. So it's not continuous change. So it is happening in this way, the step way. Okay. So this is P1 and this is P2. So P1, P2. Suddenly there is a change actually. So this discontinuity. So what happens? So at this point, so what will be the value of derivative? So let's say dp by dx. So at this point, what happens? So we have 0 actually, p1, p2. Okay. So sorry, this would be infinity. Why? Because the x point will be same. Right. So therefore, what happens actually? The differential terms cannot be applied so to capture the shock. Okay. So why? Because the derivative doesn't exist at the point of the shock. So that is the problem, major concern with the differential methods. Now when we have differential methods, in the sense what, so only let's say dp by dx. So this dp by dx, these things we use for FDM, which is finite difference method. So differential form of equations, or let's say partial differential form of equations, we are changing into, let's say, the index notation. But let us write in this way. Okay. So this one we are writing as p of I plus 1 minus p of I divided by delta x. So this formulation we are using in the FDM method. So what we have seen, so we saw a shock. Okay. So where you have sudden discontinuity. So when you take the axis, this is x-axis, this is y-axis. So this is station 1, station 2. Okay. So let's say at the point of interest P, so here at the location, what is happening? So the derivative doesn't exist. Okay. It's going infinity. So that's why the FDM method is not advisable to use. Now the one more is FVM method, which is finite volume method. The finite volume method, what we are doing, we are integrating actually. So we are using the integral form, not differential form. So when you use this integral form, let's say volume integral or surface integral, so we have the flux terms. So here you can see, so we have the flux terms. So n dot rho phi u dA and n dot gamma grad phi dA. So the diffusion and the convection term. So these integral terms are having major advantage in capturing the shock. Okay, so it's like collecting all the elements. So the differential is nothing but it's about discretizing and evaluating at particular points. So when you take the integral method, so what happens actually? So when you say integral, so when you have the collection of points, let's say you have a control volume, you have some collection of points. So the meaning of integral is nothing but, so we need to actually get the data, or we need to calculate all the points throughout the control volume. Now when we take only differential, let's say d by dv, so what you will be able to calculate at particular points. Okay, so it's a discretized one. So whereas you take integral form of equation, that will be collecting the terms. Fine. So therefore, what happens actually? So for finite volume method, so the integral form of equations are advisable to capture the shock. Now, in the previous sessions, we have seen, let's say, the continuity equation, dou rho by dou t plus del dot rho v equal to 0. So this is the continuity equation. So we need to apply the integral form of equations. Okay. So let's say we have this. Fine. So this one can be applied for this finite difference method. Now we need to use integral form of equations. Here what is happening? When we had seen the incompressible flow, so the density term is taken as constant. Okay. So what happens? So this dou rho by dou t term will vanish, and the final equation will be del dot v equal to 0. So this is the equation which we got. Fine. Now in the supersonic flow, there is no room, or let's say there is nothing like incompressible. So why? Because what happens? So let us take an example. So when we have Mach 2, fine. So what is the meaning of Mach 2? So v is equal to m into a. So velocity of object is equal to Mach number into speed of sound. So what is Mach 2? 2 into what is speed of sound? Let's say 340 approximately. So meter per second. So it is of 680 meter per second. Fine. So when we apply this reference velocity for Reynolds number, so R is equal to rho VL by mu. So the velocity of object is high, and the density also is not constant. Okay, you have higher density. So what does a shock does is, like, it will compress the flow. So here what happens, so at the station 1, let's say you have pressure P1, temperature T1, and rho 1 density and velocity V1. So if you go across the shock, so what happens, so let's say you have rho 2, you have P2, you have T2, and you have V2. Fine. So what is happening now? The P2 is very greater than P1. Rho 2 is greater than rho 1. T2 is greater than T1. So static pressure, static temperature, and the density. So at across the station 2, they are very, very higher. Fine. Next, it is decelerating the flow. What is the meaning? So let's say V1 is greater than V2. Only the flow velocity is decreased across the shock, but the static pressure, temperature, and densities, they have increased. Fine. So there is a change in density. So across the shock, what happens actually? The Reynolds number, it is increasing. So when the Reynolds number is increasing, what happens? So the diffusion term decreases. Okay. So if the Reynolds number is increased, as is increased, so the diffusion term, which is mu, or let's mu, decreases. When mu decreases, so what happens? The inertial term dominates, and the flow is maintained within certain region. So when you have hypersonic or supersonic flows, the disturbance is propagated only in specified region or certain region. Okay, so one of the advantage in the CFD is like the domain size. So let's say you have a basic example, you have a triangle. Okay, so it's like delta winglets. So if you want to investigate the triangle, So in the supersonic flow, or let's say first incompressible flow, so here the height or the spacing here, let's say this is h. So here we have to take nearly 6 times of h, 6 times of h, let's say. So here, let's say you take 2 times of h. So here you take something like 12 to 15 times of h. So this is what we have. High computation and high amount of domain is required. But whereas if you take it as supersonic flow, so this can be halved. So that by 2, by 2, by 2, by 2. Why? Because the diffusion parameter is not dominating. So it is actually less. And the domain heights, let's say the widths, it can be reduced. Fine. So this plays a some added advantage in terms of only computational domain design. But one more the complexity is, so we have a density parameter which is not equal to constant. Fine. So in incompressible flow, how many equations we like? How many variables we have? So we have pressure, we have u velocity, we have v velocity. Let's say, and we have 3 equations. But when you have the density factor coming into picture, p, you have p, you have rho, you have u, you have v. So therefore, energy equation, continuity equation, momentum equation, x, y. So these will come into picture. So when you have high hypersonic flow, we have to use P is equal to rho RT equation, such that so the ideal gas equation is used to maintain the relationship between the pressure, density, and temperature. Okay, this thing are used. Okay, so in this way, like we can conclude that so the finite difference method which we have seen is not that compatible to capture the shock. So why? Because you have a derivative term, so where you have some discontinuity approach, and whereas when you see the finite volume method, so for finite volume method we are able to capture the shock easily. Why? Because we use some integral terms, so for the diffusion and for the convection, whereas we can also visualize the shock within the control volume when we use the integral form of approach. Fine. So with this, like we will conclude this topic of FVM and FDM for shock capturing. So the next session we will see the combined effect of the diffusion and the convection for the FVM flows. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.